You got it? All right. I will begin with a word of prayer. Believe it or not. Dear Heavenly Father, we thank you for this day. We thank you for the weekend, which is about to start. Help us to just learn some linear algebra here today together, Lord. In your name I pray. Amen. All right. So let's see here. We just got done proving some really, really neat theorems about linear transformations and how they work. Now I'm going to tell you some theorems about what the set of linear transformations themselves form. So if little theorem, let's say if T and S are linear transformations, in particular T and S are elements of the linear transformations from a vector space V to a vector space W, then T plus S, defined by, how do we define T plus S? T plus S is defined in the usual way, pointwise, right? And 2, if you have C times T of x, you define that by C T of x. And of course, this is for all x in V, and this is for all x in V, and C is a scalar in the field. All right, so those are just definitions of T plus S and CT. I don't feel like I'm really obligated to make those definitions to you because I think you already know how to add functions and scalar multiply functions from some other course. But anyway, there they are. And here's the punchline. Well, T plus S is an element of L of VW, and also scalar multiple of T is an element of L of VW. In other words, let me put it into words. The sum and scalar multiple of linear transformations are, again, linear transformations. Right? Hey, is 0 a linear transformation? Like 0x equals to 0 for all x. This defines the 0 transformation, right? That behaves like 0 under addition of functions. So what do you have? I mean, another punchline. Thus, as the 0 transformation, 0 from V to W, right, is in L of VW, so it's not empty, right? That implies what? That implies that the set of linear transformations from V to W is itself a subspace of what? I'm sorry, what did I do?
Writing too small.
Writing too small. Where did I write some? My S?
No, the as.
My S looks like an infinity.
In the blue. Oh my goodness. The second you get it.
It's good? Okay. All right, let me try to recover from this degenerate font that I'm using. Now, I talked to you guys the first day we talked about vector spaces. One of our examples in our example set was the set of functions from any set to a vector space, right? So the range here of functions is W. So if you take functions from a set into a vector space, that forms a vector space, right? That was one of our original examples. In particular, we have that the set of linear transformations is in fact a subspace of this larger function space, VW. So the set of linear transformations is itself a vector space. It's kind of interesting. Another kind of transformation you could look at, another little theorem. If we have T, say, going from V to W, and if I have S going from W to some other vector space, let's say U, all right, where U, V, and W vector spaces over a field F, then the composition of these two, and so the composite, how would I do it? How about this? S composed with T, right? So where does that, it starts at V, right? Then T takes you where? T takes you to W. And then where does S take us? U, right? How do you define the composite of two linear transformations? How do you define the composite of functions? We do what? S of T of X, that's it, right? For all X in V. So there's the definition of the composite in case you forgot. All right, then, and here's really the content of this theorem. The composite of S and T is an element of the linear transformations from V to U. So let me put it into words. If you can reasonably compose two linear transformations, if they're composable, right? In other words, they have matching domains and ranges in the appropriate way, then the composite is itself a linear transformation again. I didn't prove these because they're so boring to prove I just can't bear it. This one I'll prove because it's important for you to see one of these. So here's proof. So what do we gotta do? We look at S composed with T of what? Let's say Cx plus y. And what do I want to assume? Assume that T is an element of the linear transformations from where to where? From V to W. And S is a linear transformation from W to U. Oh, I think I neglected to say something very important in this theorem, right? What did I forget to tell you? It's kind of important about S and T up here. Both linear, right? Transformations. I mean, I was assuming that. I was still so unnerved by my inability to write the word as correctly. It was distracting me. Sorry. I'll get over it, though. OK, so what's our next step? Definition. This is S of T of Cx plus y. Right? Definition of composite. And so that is what? That's S of C T of X plus T of Y. How do I do that? Since we're assuming T is a linear transformation from V to W, right? It's linear. I can pull out a constant, and I can break up the sum. Additivity and homogeneity. But S is also linear, right? So I can pull the C out now again. This is C times S of T of X, right? Plus S of T of Y. Since S is a linear transformation from W to U. See, if I was a student, I would try to think about what conversation could I have with this professor to make this become a test question. How could I put it in his brain that we should put this one on the test? Like, this is like such an easy thing to prove, right? You would like to have this as a test question, wouldn't you? Yeah, okay. Now that we've agreed that, it can't possibly be one. All right. Just kidding. Or am I? We'll never know. Oh, until we get the test, yeah, that's true. So we have S composed with T of X plus S composed with T of Y. This is by definition what? S composed with T? And then what's my finishing blow? This is C S composed with T, right? Plus S composed with T of, oh, what have I done? Oh, I'm an idiot. Why am I doing this? It was already dead. It's dead already. It's dead. It's dead. Yes, it's dead, Jim. I was debating whether it was dead Jim or if it was a dead parrot. I'm glad you went with Jim. That's a good choice. So, as dead parrots are a more obscure reference. So, yeah, there you go. That's linearity of the composite, right? And there you have it. So the composite of linear transformations is once more linear. Any questions? Okay.
Do I get bonus points for doing it as a Monty Python reference?
As we've discussed before, Adam, you would accept that you asked about whether or not there are bonus points, hence rendering the bonus points moot. You've already collapsed the wave function. What's done cannot be undone. I'm sorry. You let the cat out of the box. The cat is dead. All right, where are we? Another little theorem is that if t, and here I part ways with your textbook a little bit, okay? So you might kind of pay attention to the structure here. Suppose t is an element of linear transformations from V to W, has inverse function. And so here's the difference between me and the text. When I say inverse function, I just say inverse function in the sense of set theory. I do not suppose in my definition of the inverse function that it's linear. That to me is awkward. I don't know why your textbook does that. He has built into the definition of inverse transformation that it's a linear transformation, and that to me is awkward. So suppose you have an inverse function for this linear transformation. Then, because otherwise it's hard to say this theorem, and suppose the inverse, I need to give it a name, S. So S would be a mapping from where to where, from V back to W again, right? Then, here's the punchline. S is itself a linear transformation from W to V. So what does it mean for something to have an inverse function? What does that mean? If we say S is the inverse function of t, that gets us two things, right? What are those two things? We have t composed with S is the identity, and we also have that S composed with t is the identity. But the identity on what and what? Well, S goes from where to where? S goes from V to W, right? So this is the identity on the vector space V, whereas this one would be the identity on the vector space W. It should go without saying, by the way, I'm assuming that V and W, again, are vector spaces over a field F. So I have these two things to work with, all right? So far, so good? I'm going to suppose I have these, and we're also going to assume that T is an element of the linear transformations from V to W. For those of you who are wondering what on earth id is, it's not complicated. Id V of x is just equal to x for all x in V. It's the identity function. Like say my name. What's your name? X. Okay, there. I don't know. Identity function. Just spits back the thing again. All right. Okay, so what do we want to prove? We want to prove that S is a linear transformation. What should we do? I'm going to foolishly attempt the direct proof. We may find out that this is requiring some more ingenuity. Let's find out. So let's see here. S of Cx plus y. What do I want to show? I'd like to show that I can split it up, right? That I've got C times S of x plus S of y. That would show that S is linear. That would be it. But I need to somehow use the linearity of t to get my hands on this thing, right? So maybe just doing that directly isn't the best approach. What should I do? Maybe if I look at, let's see here. How can I do this? Where should these guys be? What's the domain of S? V, right? I guess I can look at this as, so here's a, I mean, I think what I have in the notes may be easier to read, but here I'm going to do it this way. This is the identity on V acting on Cx, Cx plus y, right? But that, by the way, is the same as S of t of S. That's no help. I'm going to cut and run on this here before I burn any more time on this particular line of attack. That's not helping me. Fine, this is why I write notes. So what I do is I say, okay, I've got, suppose x and y are elements of W. Oh, wait a minute. Have I? Oh, I got my letters all backwards. No, I don't. Yes, I do. No, I don't. Yes, I do. Oh, come on, you guys. Why'd you let me do that? Are you guys going to be kidding me? Come on, why didn't somebody stop me? Well, speak up. You guys are killing me. You leave me out. I mean, I could seriously have spent another 5 minutes before I noticed that, and then it would have been truly awful. It's just moderately awful at the moment. Okay, so yes, of course the domain and range must, domain and range in this case must flip, right? The codomain has to be equal to the range in this case, right? Because we can't find an inverse unless it's surjective here, right? All right. So suppose x and y are in W. Well, no wonder I was confused. Suppose x and y are in W, then what? Hence, there exists A and B in V such that T of A is equal to x and T of B is equal to y. Why is this true? Well, I would think it's, you could worry that T doesn't hit everything, right? How do I know that T actually gets to everything in W? Well, I wouldn't be able to say that it has an inverse function unless it was surjective, right? So we're assuming that T is surjective, meaning that anything you pick in the range, well, in this case, and anything in the codomain actually is mapped to by something in the range. In other words, the codomain is equal to the range. All right, well, with that, now we're in business, right? So then it's easy. If you look at S of Cx plus y, which are arbitrary things in W, what do you got? Well, you've got S times C times T of A plus T of B. All right? My S's are slowly but surely decaying into snakes. And then what you can do then is bring the A and the B and the C inside the argument of the T, right? Because T is a linear transformation. We got to use linearity of T somewhere because this theorem just simply isn't true if T is nonlinear, in general at least. Okay. If you go looking at nonlinear functions which have inverses, I think more often than not you'll find that the inverse function isn't the same kind of nonlinear function. Like a square root has a square as an inverse, for example, with appropriate choice of domain. Now this is what, though? Remember, S composed with T is the identity, right? And I think you guys haven't fixed my, let's see here. Are these right? Yeah, okay. Wait a minute. No, S goes first. This should be W, right? You guys have got to speak up. Uh-oh. If that's W, what's that one? Right, because T goes first, right? All right. So S composed with T is what? The identity, right? So this is just CA plus B again, right? But that is just C times T of X. Where was I? What have I done? What? Seriously? A was what? Oh. Oh. I'm sorry. A little bit more thinking here. What is A? If we solve for this, A is what? Oh, man. I'm not saying what we're doing is wrong. There's something I'm missing at the moment. I need to get back to S, right? Oh, I'm an idiot. Look, so take S of both sides here. S of T of A, right, is equal to S of X, right? In other words, A is equal to S of X. And likewise, S of T of B is equal to S of Y. Hence, B is equal to S of Y, right? So this is really C times S of X plus S of Y. And there you have it. Now we've shown that S is linear. This is pretty nice. What this means is if you have a bijection, right? If you have a function which is 1-to-1 and onto, right? So that means it's invertible. If you know that the function is linear, it's automatically true that the inverse function is linear. So you don't have to check linearity of the inverse. It comes for free by this theorem. It's pretty nice. Pretty nice result. All right, now so that brings us to let's see here. Oh, I should make a comment. So we have, I guess I could have made this comment before I butchered that theorem. It's your fault too. You didn't speak up. Every last one of you. All right. But mostly the people who understood and didn't say anything. Okay, so you know who you are. This shows that the set of linear transformations is in fact itself a vector space, right? It's a subspace of this function space. Now, if we look at a more special thing, we can look at, say, linear transformations from a vector space to itself. Well, that's even more special, right? What happens if you take, say T and S from something like that are both linear transformations on V? What if you take T composed with S? What do you get? V to V to V again, right? In other words, the composite of two linear transformations on V is again a linear transformation on V. In fact, we drop the VV here and we just write L of V because there's no need for writing two vector spaces when it's just really about one, right? And this is a very special case. If we study linear transformations from the vector space back to itself again, very nice and a very special structure here. So we get more. We have the sum of linear transformations on a vector space is again a linear transformation on a vector space, right? Scalar multiple. But we also have this other thing, right? Something new. And what you can say is that this gives us a way of quote unquote multiplying. This gives us a multiplication in some sense of the linear transformations. So this composite of linear transformations is again a linear transformation. So if you have a vector space, all right, and in addition that vector space has something called a multiplication. What's a multiplication? Well, multiplication on a vector space is something like this. It's like in this case it's, well, I don't want to find. Let me use W for just a second here. Like from a vector space W cross W back to W again is a multiplication. So a multiplication of vectors takes in two vectors and it spits out another vector again. And we're really interested in multiplications which respect also the linear structure. So, and we usually do something like this. M of A comma B, we'll just write like AB for multiplication. And usually it's assumed that this multiplication is a linear It interfaces with the addition in the vector space in a natural way. Like, for example, A times B plus C should be what? You know it. AB, AC, right? And the function composition works like that. If you look at T composed with, say, S1 plus S2, so the composition of a sum of two transformations, you'll get, in fact, exactly this. So composition and function and addition of linear transformations follows this pattern. And that makes the set of linear transformations from a vector space to itself actually what's called an algebra. An algebra is a vector space where you also have some notion of multiplying the vectors and getting back vectors again. We don't usually have a multiplication in our vector spaces, right? This is special. If you ask me how to multiply like these, I wouldn't know. I don't have a way of multiplying those, not naturally. But these I do. So multiplications are very special. It's extra structure. All right. You could even look at the set of linear transformations which are invertible, right? You could look at the set of linear transformations invertible. Those are special. They can have a name. It's called GLV. What this is linear transformations L from V to V such that L invertible. That's a very interesting thing. In fact, you can show that that forms a group in the abstract sense I talked about at the beginning of this course. Everything has an inverse. It's the inverse transformation. The identity transformation's in there. Composition of linear transformations associative. The composition of two linear transformations is again a linear transformation, right? So it's closed under composition being the group multiplication. And so this actually is in fact a group inside that this algebra. Of course, the set of all linear transformations from V to V includes things that don't have inverses, like things that are like that nilpotent stuff we looked at earlier, for example. All right, I digress. Let's get back to the. Let me stop storytelling and get to the next theorem here. We had this really nice theorem about linear dependence. What was the theorem? Do you remember? If we have a linear transformation, the image of a linearly dependent set is once more a linearly dependent set, right? So on the opposite spectrum of things, we have this theorem. If T is a linear transformation from V to W is invertible, then if S is linearly independent, well, let me state this in let me use some brackets to cheat the grammar here. Then here's the claim. If S is linearly independent, that implies then T of S is linearly independent. So invertible transformations map linearly independent sets to linearly independent sets. Let's prove it. Okay, so suppose S is linearly independent subset of V. And T. T is an element of GL V comma W. Oopsie, I guess I should tell you what that is. This is linear transformations from V to W such that L inverse exists. In other words, it's the set of invertible linear transformations from V to W. Sorry, I do a lot of name calling in here. As we've discussed, I know that some of you are Trump supporters, so you appreciate that. But let's see here. You're like, we don't care about Trump. Stop talking about Trump. All right, fine. So then what? We would like to look at, S has to be a finite set. I'm assuming it. I'm only working in the finite context right now. Let me be clear about that. I am assuming this might be true in the infinite dimensional context, but I'm really just working finite at the moment. So assume the dimension. I'll let you think about whether or not this argument makes sense in infinite dimensions. Okay. So S must be finite, right? Because otherwise it would contradict the dimensionality, right? The dimension theorems we had before. You can't have more vectors linearly independent than the dimension of V. So S must be a finite set. In particular, we can just say S is equal to S1, S2, S, let's say K. So then T of S, by definition, is T of S1, T of S2, T of Sk. It's the set of images of the S vectors. We're assuming linear independence of S, right? Consider, I think you guys will like this argument. It's really simple. C1 T of S1 plus C2 T of S2 plus plus Ck T of Sk equals to 0. What would we like to show here? Man, time flies when you're having fun. Curses. We want to show what? What is our goal? We want to show C1 and C2 and all the way through Ck is 0, right? Now we can use the theorem we proved last class, which is what? This implies what? This implies T of C1 S1 plus C2 S2 plus plus Ck Sk. Remember we proved this by induction last time? So that implies this, right? And then you got choices. I mean, to complete this, well, we said T was invertible, right? Which means it's injective. So if T is injective, then what? The only thing in the kernel is 0. That must be 0. You could do it that way. Here's another way you could do it. You could just calculate, you could take T inverse on both sides because we're given it exists, right? You could do that. It's another way we could proceed. How do you guys want to proceed? Inverse? All right. So T inverse of T of C1 S1 Ck Sk is equal to C1 S1 plus Ck Sk, and that's equal to T inverse of 0, but we just got done proving what? The inverse of a linear transformation is a linear transformation. Therefore, T inverse of 0 is again 0, because linear transformations map 0 to 0. First thing we proved, right? So then, what do we get? By linear independence of the S set, we conclude C1 equals 0, C2 equals 0, and so forth. Ck equal to 0. Any questions? Hopefully not about what I was erasing. All right, let me tell you where we're going. I have a section where I have this list of examples that we can look at. You can actually see what linear transformations do in specific examples going from R2 to R2 for various choices of matrix. All right, and I've got some examples of how the the linear transformation either will like kind of either preserve the dimension of something in the domain to something in the range, or it'll squash dimensions. All right, and so I have this long laundry list of examples, which I might project here in a bit, and then I discuss the fundamental theorem of linear algebra. That's the next thing theoretically on our docket. Past that, we need to talk about the extension and restriction theorem, coordinates, isomorphism, and there's still a little more theory past that. Obviously, I can't finish that today, right? There's at least one more day on linear transformations. So I think what I probably should do is I should prove the fundamental theorem of linear algebra. So here it is. Stupid snow. It's got me all off kilter. All right, L, a linear transformation from, say, Fn to Fm. A function, let's say, then L is an element of the linear transformations from Fn to Fm if and only if L of V is equal to AV for some matrix A in Fm by n, and that's, of course, for all V in Fn. So what this theorem says is that linear transformations of column vectors can be rewritten in terms of matrix multiplication. We'll come back to this abstract world of linear transformations in a bit. We have to talk about these concrete things here for a little bit. Okay, so we proved one direction to this already, right? In particular, I told you one of our first examples, I said, hey, if the formula is a matrix multiplication, that implies it's linear, right? That in fact I already did. It's not hard. You just put in like CV plus W here, put it here, properties of matrix multiplication, split it up, it's linear. Not a big deal. The other direction is a little bit more interesting, so let's look at that. So I needed some notation. Let's let Fn be the span of, let's say, EI, I equals 1 to n. Maybe I should say j equals 1 to n. And let's let Fm equal the span of Fi, I equals 1 to m. Now these are both the standard basis vectors. It's just one is n vectors and the other is m vectors. I just want to use a different letter because I have one has one length and one has the other length, and I want to distinguish them. So I don't want to use E for both. Is that okay with everybody? Do you understand what I'm doing? These are just the column vectors that have 1 in the either ith or jth spot and 0 everywhere else. Those ones, right? Okay, so assume that L, a mapping from Fn to Fm, is linear. What would I do?
Oh, no, I was just wondering why there was a separate here. Like it was biconditional and then there was a...
Oh, this refers to the, what I'm saying is last, previous class we proved that direction. It was one of the examples we looked at. I presented as a theorem just that implication. I haven't proved the other implication yet, so a fair question. So then what? Well, what does an arbitrary thing in the domain look like? Notice this. If V is an element of Fn, then we can write it like this. V is actually equal to a sum I equals 1 to n, or I say j, I guess j equals 1 to n of what? Of Vj, Ej, right? Standard basis expansion. We talked about this before. And the Vj's are, scalars in the field. So let's look at this. Then we've got L of V, right? That's equal to L of the sum j equals 1 to n of Vj Ej. Okay, but this is linear, so we can pull out the sum. We proved that by induction last time. All right, linearity by linearity. Now, the next move is a little bit sneakier. L of Ej, where is that? That's an element of Fm by construction, right? L is a mapping from n vectors to m vectors. M vectors are the range. So for each j, that's some vector in Fm. So I can expand that, right? In terms of components, I can expand that in terms of the little f's. So that tells me that I can write L of Ej as equal to, sum I equals 1 to m of some numbers, let's say Aij. Convenient. Fi for some Aij's. In the field. Again, that's because if L of Ej is an m vector, it has to be in the span of F1 through Fm. It's a standard basis. It spans everything there, right? Okay. Okay, so put that together. We got sum over j equals 1 to n, Vj sum I equals 1 to m of Aij Fi, and then you just write this sum I equals 1 to m using properties of finite sum j equals 1 to n. I can flip their order, and I can bring this constants inside, and I've got myself a I j Vj like that. But that is nothing more, this right here, right, is nothing more than the matrix A times V, the ith component of that. And so this is altogether nothing more than A times V. So this simple calculation shows you any linear transformation of column vectors can be written as a matrix multiplication. How is the matrix defined? By the way, this A is special. Definition: A is the so-called standard matrix of L. I can be a little bit more explicit. Definition: the standard matrix of L is equal to, what it is it's L of E1, L of E2, L of En. There's a column definition of it. If you want, over here, there's you could also say this, the jth column of the matrix, standard matrix of L, okay, the ith column of that. Oh, let me just stop. This is enough. I don't have to tell you 13 different ways to define it. They're in the notes. That's a good way. It's also implicit over here. This gives you another way of defining the Aij. Okay. So an example. If I have, let's say, L of x comma y equal to x plus y, x minus y, and x. All right. I can easily find the linear, the standard matrix of this. That's L of E1, L of E2. In other words, L of 1, 0 and L of 0, 1. What are those? Plug in x equals to 1, y equals to 0. What do I get? Don't forget, this is my sneaky notation. That's actually a column vector in disguise, right? So it's good to write that. It's helpful. So plug in 1, put y equals to 0, we get 1, 1, 1. Plug in x equal to 0, y equal to 1, we get 1, minus 1, 0. There you go, standard matrix. I think you guys can find standard matrices, right? This isn't a bad part. All right, so properties of the standard matrix, they're really nice properties. If we have two column transformations, the standard matrix of a sum is the sum of the standard matrices. That's pretty nice. The scalar multiple of a linear transformation is C times the standard matrix. So this, of course, in order for these to make sense, these are all in column vectors, okay? Not abstract linear transformations, but what I would say concrete linear transformations, ones that are going from column vectors to column vectors, okay? There's more fine print that's required in the case we talk about abstract linear transformations. They'll do that next class. Or maybe I'll post a video, I don't know. We're behind. All right, so what do we got? And then this is the more interesting part. The composite of two linear transformations. What's the matrix of a composite of two column vector transformations? It, in fact, is the product of the standard matrices of the composite. Truth be told, this is why we defined matrix multiplication as we did. Precisely so that this identity right here happens. Okay, so that function composition and matrix multiplication interweave in this natural way. Let me just try to prove this last one. All right, let's work that out. The other two are really, really easy. So how would I prove such a relation? What I would do is I would look at T composed with S, right? And I would look at, say, EJ. I'm going to assume that they're composable, right? So that they have the matching, they're going from the right size domain and codomain. Let me just not belabor you with those details here. They're in the notes. So assume this makes sense in short. Now that would be what? This would be, I mean, this is what? This is column J, right? Column J of the composite standard matrix, right? That's, I mean, if you condense this down, what that says is that the jth column of the standard matrix is L of EJ, right? That's the same thing, just written concisely. So then what? This, well, that is nothing more than T of S of EJ, right? Definition of composite. Okay, so what's S of EJ? Well, that's the standard matrix of S times EJ. I mean, if you go back to here and you look at this in terms of the notation we've introduced, you would erase this A, right? And you'd write in L bracket like that in retrospect. So by the fundamental theorem of linear algebra, that is S, the standard matrix of S times EJ. But then we just do this again for T. And we've got standard matrix of T times the standard matrix of S times EJ. But by the way, what is any matrix, right? Think about the product of bracket T and bracket S is itself a matrix, think about this thing as M, quote unquote. What is M times EJ? By our fundamental study of matrix multiplication earlier this semester, that is precisely the jth column, right? That's column J of M, remember? So this is column J of the product of T and S. If these are equal for arbitrary J, that means every column matches. Consequently, these are the same matrix. And that proves, let's say, part 3 of this proposition. Does that make sense? I hope so. Ah, man, there's so much I want to tell you guys. But then there's the weekend. Have fun. So the homework is due next Friday. Hopefully I think I'm going to post a video for the sake of you being able to get further in the homework this weekend. I'll try to post basically the next lecture as a video so that we're not, because we're going to get snowed on again. I can feel it. It's going to happen again. You know it's coming. Well, I mean, I love snow, but I love linear algebra.